Okay, so now let's take a look at epoxide under acidic conditions. So right here, this part right there, under neutral and acidic conditions, we need to scratch that out and just say, okay, reactions of epoxides under acidic conditions. All right. Now this molecule here was from the last video, and so now we're going to see something so cool. The regiochemistry is now going to swap. Okay? But we have to look at the mechanism. Let's use the mechanism to help figure this out. So under acidic conditions, what is the first step going to be? It's going to be a proton transfer because we have an acid. And so the lone pair here is going to come and protonate that epoxide. So if we protonate that epoxide, what do we have? We have an oxygen like so. And we still have our methyl. Let's see if it's cutting off. It is cutting off. So let's do this again a little further up. All right. Let's see. Is that better? Yeah, that's better. CH3 like that. Okay. So the first step was we protonated that oxygen in the epoxide ring. Okay. And that looks pretty messy as well, doesn't it? So this was a proton transfer. Okay. Now when we do a proton transfer in the first step under acidic conditions, protonating that oxygen is now going to weaken one of these bonds right here. So we have carbon 1 and carbon 2. And the epoxide has a choice. Because this oxygen has 3 bonds, it's unstable, so it wants to break one of these bonds right here between carbon 1 and the oxygen or carbon 2 and the oxygen. And it wants to do that to gain more stability. But which one is it going to partially break at the very beginning? Okay. And what's going to happen is that it's going to partially break this carbon-oxygen bond right here. And I'll explain the reason why in a minute. But this bond right here is going to be partially broken. Still there, but partially breaking. And I'm going to represent that with some dotted lines right there. Okay. And so what happens now is that we have bromide floating around. Okay. Bromide floating around after that proton transfer step. And so that bromide is going to attack the more substituted carbon. And it's going to do it from the opposite face of where the oxygen is. And then this bond right here is going to fully break and giving its electrons to that oxygen atom. So what do we have to do? Draw carbon 1 and carbon 2, leaving the wedges and the dashes as shown. CH3, wedged ethyl. Where did that bromide come in? It came in from underneath. What's on the top face? The oxygen. Like that. And then we have carbon 1, and we still have our CH3, our hydrogen that's not shown. We can draw it in right there. And there it is. That's the reaction. That is the mechanism. What was this step right here? That was a SN2 mechanism. So let's take a look at the stereochemistry now. Look at what's happened here. That is an R, that stays an R. This was an S at carbon 2, but we did backside attack, so that's going to invert that stereocenter. It's not inverting the stereocenter at carbon 1. So pretty slick. So in summary, under neutral or basic conditions, the attacking species is going to attack at the less substituted carbon due to a steric argument. Under acidic conditions, the attacking species is going to attack the more substituted carbon. And that is due to an electronics argument. Okay? So let's talk about that electronics argument next. So if we have ourselves a protonated epoxide, and I'm just going to represent, let's look at this epoxide here, okay? And I'm going to protonate it like there. Now, like I said at the beginning of the video, when it's protonated, one of these carbon-oxygen bonds are going to be partially broken. And the epoxide makes a choice. And it's going to choose this, if we number it, it would choose to partially break the oxygen carbon 2 bond. Okay? Now, why does it do that? Well, let's just think about it in this way. What if I take that epoxide, draw it again, okay, this is not what happens. This is just all hypothetical. Okay? If we break the oxygen carbon 1 oxygen bond, let's say if we just completely break it after it gets protonated. If we completely break it, now I'm being very clear on this, it doesn't happen this way. We would get what? A primary carbocation. Right? Let's contrast though. What if we decided to completely break the oxygen carbon 2 bond? We would get a carbocation there, and then we would have a secondary carbocation. Between these two options, which carbocation is the most stable? Clearly the one on top, right? So this does not happen, but this explanation helps us to understand why the epoxide is going to choose to partially break this bond instead of partially breaking that bond. And the reason why it chooses to partially break this bond is because we are going to have a more stable partial positive charge on that carbon instead of having the partial positive here. We're not going to have a full-blown carbocation because this bond still exists, but it's a partial positive. And then on this one, we're going to have just a tiny partial positive because the epoxide is going to preferentially have this bond be the partial bond because it gives us a more stable partial positive because of the donating ability of the alkyl groups. Remember, alkyl groups are electron donating, whereas on carbon 1, in this example, there's only hydrogens. So if you don't remember this word, hyperconjugation, highly encourage you to go look at that word and study up on what it means in relationship to the stability of carbocations. Right? And so that's why under acidic conditions, the attacking species is going to attack the more substituted carbon because there is a larger partial positive. And so that nucleophile, which is negatively charged in this example, is going to feel a stronger attraction to this larger partial positive than to this tiny partial positive. Okay?